All right, everyone, good afternoon. Welcome back to our MSD 780 postgraduate dynamics lectures. Today we're going to start with the second study theme, which revolves around using the simple pendulum rod to essentially show and give you an indication of the multibody dynamics principles that we're going to use later on in the DAP-BC workbench. Before we start with that, perhaps just a quick review of the introduction lecture that we had previously, essentially an introduction to planar multibody dynamics. So in section 1.1, we explored multibody mechanical systems. We said these mechanical systems can usually be broken up into either simple mechanical systems where you have something like a single pendulum rod, so something that's very simple in terms of the number of bodies, the number of kinematic joints that we have available, or you can go essentially more complex with your multi-body mechanisms, which is essentially defined by more bodies, more compliance elements, kinematic joints, those kind of things. With regards to the types of analyses, we essentially looked at statics and dynamics. We said statics is more focused around equilibrium calculations, so a system that is either at rest or doesn't have any changes in velocity, so there's not really an acceleration in the system. But we are more focused on dynamics and specifically kinematics, and then also the outbranching of the actual dynamics. So kinematics, which is focused around the actual motion of the system without considering forces, and then dynamics, which then takes into account the effect of forces on the motion of the mechanism. With regards to the methods of formulation, we also had a look at a few examples over there. We said, firstly, if we consider classical methods, they are usually hand calculations or calculations that require us to construct some geometry for specific configurations of systems. So I think the example that we looked at over there was slider crank mechanism. So simple three-body mechanism, and we essentially had a single crank angle, and we were able to actually go and draw the schematic of how the position analysis, the velocity, and the acceleration analysis looked. Then we also looked at some more modern solution techniques. So these are simply making use of computational and numerical resources to investigate the variation of some parameters. So previously, where we had for the slider crank mechanism an angle of 30 degrees, now we can go and vary it, and we can say if the crank angle varies from 0 to 90 degrees, what effect will that have on the kinematics and the dynamics of the system? And that is where the computational power of a PC and the workbenches and the type of software that we use really comes into play. Then finally, we just had a look at the actual computer programs that we have available, and we essentially looked at the case where we spoke about a special purpose program or a general purpose program. So special purpose program tends to run a bit faster than your general purpose program in the sense that it has a very dedicated multi-body mechanical system that it can solve. If I do, however, make any changes to this multi-body system, I suspect that all of the analyses or the calculations and the equations that went into the original special purpose program will need to be retrofitted for the changes that I make to the mechanism. Whereas with a general purpose program, although it runs slower, I can plug in essentially any type of multi-body mechanism and it can solve it without me having to worry about re-deriving some of the equations. The reason why the general purpose program also runs a bit fast or a bit slower, is simply because it can generate a large number of equations even if you have a very simple mechanism. So even something as simple as a pendulum rod, it's still going to run a bunch of equations that it has to solve, even though it's much simpler than, let's say, a 7 or 10 body mechanism that I want to solve for. All right, so that was just a brief review of what we looked at in our introduction lecture. So I'm just going to close that. And today we are going to jump into the second study theme. And it's essentially focused around using the pendulum rod to explain all of the underlying principles that we're going to look at in Nikravesh's PMD textbook, specifically from a body coordinate perspective. You'll later on see we do have a few other formulations that Nikravesh also proposes in his textbook. I believe it's point coordinate is the other well-known formulation as well. But for us, the body coordinates formulation is essentially going to form the basis of our DAP-BC workbench that we're going to look at once we delve into the application example study theme. Right, so starting off with section 1, just perhaps giving you a quick review as well of Newton's laws that we are going to apply. And essentially, we're going to apply all 3 of Newton's laws whenever we perform some sort of a multibody analysis. Now, I think by now you're all well acquainted with Newton's 3 laws. Just to give you an overview again, Newton's first law is essentially a simplification of his second law, which simply says that if a system is not acted upon by any net or external force, that system will remain at rest, or it will continue to move at a constant velocity, so there won't be any acceleration effects on the system. Newton's second law takes this a step further and simply says that if I do have some external force, that or a net force that's acting on the system, that net force is directly proportional to both the mass and the acceleration of the system. And Newton's third law, in the most simplest terms, simply states that every action has an equal and opposite reaction. So now I have 2 bodies that are, let's say, colliding or interfacing with one another. The force applied on one body is equal to the force applied on the other body, but just in opposite directions. And Newton's third law is essentially going to come into play when we start looking at the kinematic joints. And I think today we're going to look at the revolute or the pin joint specifically, which is a good example to start off with Newton's third law and the formulations applied over there. All right, so PMD section 4.3.2 focuses on the centroidal equations of motion. And these are the type of equations of motion that we're going to focus on as well whenever we do our analysis. So the equation of motion for the mass center of a rigid body is directly obtained from Newton's second law. And this simply states that m r double dot is equal to F. And you'll notice r double dot and F are both in bold. That is simply because these are 2 vector formulas that we use over here. So r double dot can be broken up into the x and y component. So x double dot, y double dot, and f can then be given as fx and fy, which is then your external force vector that we have available. So m is simply the mass of the body, r double dot is the vector of acceleration of the mass center, and f represents the vector sum of all external forces acting on the body. Now, for planar motion, in addition to the 2 translational degrees of freedom that a free body exhibits on a plane, a free body also exhibits 1 rotational degree of freedom. So this is essentially just a reiteration of Newton's second law just with regards to rotations. So the rotational equation of motion of a body is described as J phi double dot equal to N. And in this case, J is the mass moment of inertia. This is usually given in kilogram meters squared. Of the body about its mass center, and this is also very important. You'll see, I think perhaps from your mechanics of materials textbook as well, you do have some standard formulas available for, let's say, rods or rectangular sections, and usually they give it either about some endpoint or they give it about the mass center. For our case, since we're working with the centroidal equations of motion, J is also always taken around the mass moment of inertia. So whenever you use those formulas, just make sure that you're using the formula that is about the mass center of the system. Then phi double dot is the angular acceleration of the body, and N is the sum of all the torques and the moments of all forces with respect to the mass center that acts on the body. So throughout the PMD textbook, Prof. Nikravesh also uses the term moment of inertia to simply refer to the mass moment of inertia about an axis. And this axis is then perpendicular to the plane and going through the mass center unless stated otherwise. If you are also interested, you can go and look at proof 4.2 in PMD. This is simply where Nikravesh derives the rotational equation of motion for a planar rigid body, as we describe it over here in equation 4.14. In our case, we're not too interested in the actual proof. We just need to note that this is one of the one of the important equations whenever we perform planar multibody dynamics. We essentially have translational equations of motion in the x and y direction, and then we have a rotational equation of motion about the z-axis, which is then perpendicular to the plane in which you're working. Now, if I go and combine equations 4.13 and 4.14, I can essentially put it into matrix form as I have over here in equation 4.15. So over here to the left, so this first matrix that I have over here is simply the mass matrix. So you'll notice it's a diagonal matrix. The first two elements are simply the mass of the system, and then the last element that I have over here is the mass moment of inertia. Then I multiply this with my acceleration vector. So this is r double dot expanded, so it's x double dot, y double dot, and then I have this final 4.14 equation, phi double dot, that I also plug in over here. And this should all be equal to the external forces applied in each of these directions. So the first element is then equal to fx. Then I have fy for the y direction, and n is simply the sum of the moments about the z-axis. If I want to, I can also go and write it in a bit of a more simplified form. In this case, I simply use the identity matrix, which is then going to be a 2 by 2 matrix with diagonals being equal to 1. So I can then write this as a 2 by 2 sort of matrix as well that can be expanded if I need to. And this is then where I also simply combine x and y double dot, and this is why I get this r double dot over here. And in its simplest form, I end up with this mc double dot, which is equal to h. C double dot is then r double dot phi double dot, which is the centroidal array of accelerations. H is the centroidal array of forces, and m is simply known as the mass or inertia matrix of the system. Now, equation 4.15 is referred to as the centroidal equation of motion because the reference point on the body is its mass center. In the PMD textbook, the term equations of motion or dynamic equilibrium equations will be used to refer to the centroidal equations of motion unless specified otherwise. It's just a generalization of what we would normally call the centroidal equations of motion. Right, so that's a quick overview of how we're going to apply Newton's second law. Perhaps, before I continue with section 2, are there any questions at this stage, feedback or concerns that you may have before we move on to section 2? All right, so just like I said last time as well, if you have any questions, feel free to just pop them under the chat messages and I'll get to them as I work through our lecture material. But at the moment, it doesn't seem like we have any questions. So in that case, I'm just going to continue on to section 2 then. And this then revolves around what the influence of joints are on multibody dynamics. And you'll remember from section 1, I said that this is where Newton's third law comes into play. And this is more elaborated on in section 4.4.2 of the PMD textbook, where we specifically look at reaction forces. So when kinematic joints are present in a multibody system, we must consider their corresponding reaction forces and or torques in the equation of motion. And Newton's third law of motion between two particles can directly be correlated with the reaction forces due to kinematic joints between two bodies. Reaction forces or torques act between two bodies along or about the axis for which no relative motion is allowed. And a kinematic joint removes one or more of the three relative degrees of freedom between two planar bodies. Now, when we refer to the degrees of freedom in 2D, essentially what we're talking about is X and Y translation. So each of those are 1 degree of freedom. So if we look at translation in X and Y, we essentially have 2 degrees of freedom. And then we can also allow rotation about the Z-axis. And that is then known as our third degree of freedom. So what a kinematic joint essentially does is it connects two bodies at the expense of removing 1 or 2 or all 3 degrees of freedom between these two planar bodies. The imposed restrictions on these relative motions are then expressed analytically, and we can call them constraints. So let's consider the two bodies connected by a pin joint, shown in figure 4.10a. So we have bodies I and J, and between them we have this revolute joint situated over here. So in the case of a revolute joint or a hinge joint, we essentially allow rotation in the z-axis, but we don't allow translation between the two bodies. So a pin joint allows the bodies to rotate relative to one another, but it eliminates the relative translation between the attachment points along any two orthogonal axes. And usually these orthogonal axes are in the global xy frame. So with x being to the right, y being upward. Since this joint removes two relative translational degrees of freedom, the resultant reaction force on each body can be described with two orthogonal components, λ1 and λ2. Whenever we remove a degree of freedom, we need to remember to place either a reaction force or a reaction torque in the degree of freedom's direction. So in our case, since we're removing x and y translation, we place reaction forces in the x and y direction. All right, I think that was a brief overview as well of the revolute joint. We're going to, once we now jump into section 3, we're going to expand a bit on the pendulum rod and how the revolute joint is handled over there. But section 3 is then also according to the free body diagram methodology, which is explained in the PMD textbook chapter 6. Now the pendulum rod that we are considering is schematically represented in figure 1. This figure that we have over here, and you'll notice that we have the pendulum rod which is connected to ground via a revolute joint over here, or a hinge joint. And we also, for simplicity's sake, we just place the global coordinate system at this grounded revolute joint as well. And on the body itself, you'll notice there is a local coordinate system. So this is the xi eta coordinate system that we have over here, and we're going to delve into local coordinate systems in a bit, but just take note that we essentially have two different coordinate systems, a global coordinate system and a local coordinate system. Now, in addition to the pendulum rod schematic that's given, we also have some mass and inertia characteristics that are given. So the mass of the pendulum rod, which is 2 kilograms, and then J2, which is the mass moment of inertia, and this is about the centroid, so about the center of mass. If we calculate this using the formula that we have available either in our, let's say, mechanics of materials textbook, or I think you can find these formulas online as well if you just type it in, you'll essentially end up with this 1/12 ml squared equation that you have over here. And if I plug all of the values in, I get this 0.06 kilogram meter square value for J2. I think it probably would have been better to call this J1 and M1, simply because we're working with a single body. Ground isn't considered a body. We usually call it body 0. So in our case, we could have also, instead of just calling it M2 and J2, we can also just use M1 and J1 since we're working with a single body. Now in the configuration shown in figure 1, the following coordinates are also provided. So R1G is simply a vector showing the location of the center of mass. And to understand how we get this, we essentially just have to look at this figure 2 that we have over here. So here they actually give us the angle 30 degrees. And since we now know that the length of the pendulum rod is 0.6 meters, we can go and find the location of the centroid, or the center of mass, just using basic trigonometry. Now the free body diagram of the pendulum rod mechanism is then shown in figure 2, and this is essentially where we break up the pendulum rod from ground. So since I'm doing that, I need to remember that there's a pin joint that exists between ground and the pendulum rod. So I just need to add the two translational reaction forces over here. So this is λ1 and λ2. It's typically good practice as well when you set up your free body diagrams to make sure that if you specify λ1 to the right and λ2 upward, for example, on ground, then on the pendulum rod, just do it in the opposite direction as well. This is essentially just Newton's third law telling us that the reaction is equal and opposite. Equal in magnitude, but opposite in direction. Now, the components of the reaction force for the pin joint are marked as lambda 1 and lambda 2 in figure 2. And the components of the reaction force are indexed consecutively for easy reference. Based on the free body diagram of figure 2, we also construct the arrays of reaction force and then the equations of motion. So to do that, we simply remember from the previous section that we looked at, we have some sort of a mass or inertia matrix that we construct over here, diagonal matrix. In reality, you have a bunch of zeros over here, but we're only interested in these diagonal elements. So if I construct this, I have in the first two entries, I have the mass of the pendulum rod, and then the last entry is the mass moment of inertia, 0.06 kilogram meter squared. Then I have my acceleration vector, so this is x, y double dot, and then phi double dot, which is then equal to, and all I did over here was essentially break up the reaction, or not the reaction forces, but the external forces that are acting on the system. So this first vector that I have over here is simply gravitational effect, so gravity acting in the negative y direction. If I multiply 9.81, which is the gravitational constant, with the 2 kilograms, I get this minus 19.62 value over here. And then I just plus the reaction forces over here for lambda as well as the effect of the moment in this last entry, or this third row that I have in my matrix setup. So remember now, for the pendulum rod, lambda 1, lambda 2 are acting to the left and downward respectively. So in my global coordinate system, that is essentially negative values. So negative lambda 1 and minus lambda 2 as well. Now, if I go and look at the final entry that I have over here, which is then simply the net moment acting on the system, I'm going to take it about the center of mass. So if I look at the effect of lambda 2, I essentially break up this vector that I have over here from the center of mass to point A, where the revolute joint is. I break it up into its x and y components. So in this case, I essentially end up with lambda 2, which is going to give me a counterclockwise moment. I just have to multiply by the moment arm, which is this 0.259808. So that's why it's positive over here. I see it is a bit cut off over here, but it's essentially plus 0.259808 lambda 2. And then if I look at lambda 1 as well, together with its moment arm, it's 0.15 times lambda 1, and it's also going to create a counterclockwise moment, which is considered positive in our global coordinate system. So once again, it's going to be plus 0.15 lambda 1, and I simply add them together for my net moment. All right, then the reaction force from the pin joint that acts on body 1 has a moment arm S1A. So this is the vector that I spoke about earlier. This vector is constructed from the center of mass to point A over here, where the revolute pin is located. And we simply denote that as S subscript 1 to indicate it's from the center of mass of body 1, and then superscript A, which is then the actual point that I'm considering. So the reaction force from the pin joint that acts on body 1 has a moment arm S1A, which results in a moment in the rotational equation of this body. The moment associated with the reaction force is then determined in this form over here. So I simply use my moment, which is in vector form equal to R cross product F. So in this case, S1A is the R vector that I'm considering. I cross this with the actual F or reaction force vector that I have over here. So in this case, the negative sign over here is a bit misleading. It makes it seem like we're taking whatever system we've defined over here and multiplying it by -1. In fact, it's easier to just say S1A cross product lambda 1, 2. And then when you set up your multiplication of the cross product, you just go and check in which direction is lambda 1 and lambda 2 acting. Now, in this case, we can see it's to the left and downward, so it has to be minus lambda 1 and minus lambda 2. And that's how I denote it in this system over here as well. And if you now go through the actual cross product, so you multiply out, you should get this, this equation k hat over here, which is essentially the same as what we defined in equation 1 that we have available. All right, now in algebraic form, this cross product can also be expressed as S1A prime rotated. So what do I mean by that? S1A we now know is from the center of mass 2.A. Prime simply indicates that it's the transpose. So previously where I had, I think it was a column vector, I just changed it now to a row vector. And then this concave symbol that I have above the S means that I essentially rotated the system. And we're going to look at that in just a moment, but just take note of the rotated symbol that we use. So if I then equate this, I essentially get S1A cross product lambda 1, 2 just in its multiplication form over here. And it's still going to give me the same answer as what I got in equation 1. So we notice that S1 prime A rotated is equal to minus 0.15 and minus 0.259808. So it's a bit different to what we had previously. So that these two elements that I have over here is S1A in its original form. I essentially rotated it. So what I do is I consider a vector A, which I rotate 90 degrees in the positive sense, so in the counterclockwise direction. And this is then denoted as A rotated, or A with a concave symbol above above the head of the vector symbol. And just schematically, this is essentially what happens. So I have a vector A with components A1 and A2 in the 1 and 2 directions shown over here by the coordinate system. If I rotate it 90 degrees, I end up with A rotated, which now has components minus A2 and A1. All right, so the components of A rotated in terms of the components A are simply minus A2 and A1. So if we now think of this in the X and Y direction, it simply means that if I break my vector up, my original vector, into its X and Y components, what will happen is if I rotate this vector 90 degrees, the X component will become the Y component will become the X component, and I just need to remember to multiply the X component of the rotated vector by -1. All right, so that's just a bit of vector manipulation that we're doing over there, just to make it a bit easier for us to go and calculate the moment if we know what S1A looks like in its native form. And then the next point just regards itself with the array of reaction forces that we can express in another form as well. So we have minus lambda 1 minus lambda 2. We have our moment, net moment over here, which essentially then becomes this broken up matrix that we have over here. So lambda 1 and lambda 2. And if I then just look at the coefficients of each of these, I can go and assign them in its own coefficient matrix, essentially. So the coefficient matrix, which is then minus I and this minus S1 prime A, rotated of the reaction force, is the transpose of the revolute joint constraint Jacobian matrix. And this is explained in more detail in PMD chapter 7. So in our case, we don't need to be too concerned with how it was derived or what the actual Jacobian matrix looks like. This is usually performed, or this matrix is generated computationally. We just need to take note that this simply relates to the actual Jacobian matrix. And once we start looking at more complex systems, the appreciation of the Jacobian matrix being calculated computationally really becomes evident. But just note that the Jacobian matrix is also going to be very important in our analysis that we're going to look at. All right, so that was quite a lot of mathematics now for this chapter 6 free body diagram methodology that we're looking at. But in general, you won't have to remember any of these mathematics. It's just to give you a breakdown of how we systematically generate the equations. We essentially start with our native definition of the equations of motion, and we can expand this to vector form, and we can use these vector manipulation techniques to essentially perform all of our calculations in a numerical or computational environment. Now, before I continue on to section 4, are there any questions at this stage? All right, so I don't see any questions so far. In that case, we can then jump into section 4. And this then deals with the analysis of the pendulum rod according to PMD chapter 7, and specifically the body coordinate formulation. And this is essentially where we start drawing the lines or connecting the lines between the body coordinate formulation that we're now going to use in a very analytical manner and the body coordinate formulation that's going to be used in the computational environment when we start using the DAP-BC workbench. Just to perhaps give you an explanation, the DAP-BC essentially stands for a dynamic analysis program with body coordinate formulation, the BC referring to body coordinate. So all of the formulations that we're going to look at now in section 4, and if you want to go and look at it in the PMD textbook, it will be section or chapter 7. All of these formulations are essentially related to that body coordinate formulation. Now, starting with PMD section 7.2.1 and having a look again at the revolute or pin joint. Just going to scroll up over here. Now, we previously mentioned that whenever we have some sort of a kinematic joint, it's going to remove either 1 or 2 or all 3 degrees of freedom that's available between two bodies. And we said these degrees of freedom that are removed are essentially constraints. And in this part, we're now going to focus on the actual constraint equations and how they're set up. Now, constraint equations for a revolute joint in the body coordinate formulation can be constructed fairly easily. It's one of the easier types of joints that we have available. As shown in figure 7.3a, which is this figure that we have over here, for a pin joint to exist between points Pi and Pj on bodies I and j, their x and y coordinates must be equal, such that we essentially construct a vector where rjp is equal to rip. So these two vectors that are constructed over here, rip and rjp, essentially lie on top of one another. And this is evident when we combine the two bodies with one another. The pin essentially goes through both points Pi and Pj on bodies I and j respectively. So that's why we can make this, we can essentially enforce this vector equation over here. So therefore, the constraint equation for a pin joint is simply stated as in 7.14. So phi R2 is equal to RIP minus RJP, which must be equal to 0. So we essentially just take one of these components over, in this case, I think it's RJP, which we take over to the right-hand side, and this should then equate to 0. Now, the phi is usually the Greek symbol that we use for constraint equations. However, the superscript it gives us a bit more information relating to what type of joint we're working with and how many constraints we're enforcing. So the R tells us that we're working with a revolute joint, and the 2 tells us that we're enforcing 2 constraints. So we're removing 2 degrees of freedom between two bodies. Now, in our case, the pendulum rod is connected to ground. Hence, equation 7.14 simply becomes phi R2 is equal to 0 minus RJP, which is then equal to 0. Remember that a grounded body, or simply ground, cannot move. So we don't expect, in this case as well, for a vector to be constructed over there. Also because we have this global coordinate system, which is actually situated at the revolute joint A. So R1A is essentially 0 in this case. Now, if we want to relate phi R2 equal to 0 minus RJP equal to 0 to figure 2, we can simply write phi R2 is equal to 0 minus R1A. So we just specify what body we're working on. That is body J. In our case, it's body 1. And then P is the actual index of, or the denotion of the actual point that we're considering. In our case, it's point A. That's where the revolute joint resides. And then we did mention that the left superscript R is for revolute, and 2 denotes the number of algebraic conditions introduced by this joint. So the number of constraints introduced, essentially. All right, now to have a better understanding on how the coordinates of bodies I and J have become dependent on each other through this kinematic joint, we can use equation 3.10 to express equation 7.14 in its matrix form. So this is then given as xi, yi, which is our first component. This is simply the vector of where, relative to the global coordinate system, is the center of mass of body I located. Plus, and then we have some sort of a transformation matrix over here, which uses the actual angle of the body. And this is then related to what we call a local coordinate system. So that is denoted by this xi eta that we have over here. So xi eta is the usual denotion of a local coordinate system. Where previously we had x and y, we now just have xi and eta. And then I simply say minus, and I do exactly the same for the second body. So this is just an expanded version of equation 7.14. Now, equation 3.10 simply says that RP, so if I quickly jump over to figure 3.5, RP is simply a vector taken from the global coordinate system's origin to point P directly. And this is equal to R plus A, and then you have this S strike through P. So S strike through means that we're working now with a local coordinate system. What do we mean by this when we consider figure 3.5? So RP, we said, is constructed over here from the origin of the global coordinate system to point P. And this must be equal to this R vector plus this SP vector that I have over here. Now, as shown in figure 3.5, vector SP is defined on a body to locate point P from the body's origin, so from the local coordinate system's origin. The component of SP in the xi eta and xy frames are denoted as follows. So this is where the S strike through P comes in, so the local position of point P, which is equal to SP xi and SP eta. And we can simply write this as xi P and eta P over here. And then SP, which is the original case that we have, is simply in the XY coordinate system. So if we don't have a strike through, we're working in the global coordinate system. If we do have a strike through of the letter, it means we're referring to the local coordinate system. And we can then go one step back, and we can essentially relate the xi eta and xy components to one another through the transformation matrix A. And this is then SP, which is equal to this A S strike through P. And essentially what we do over there is we consider the angle then of the body. And this is where the cosine phi and sine phi components come into play when we relate these components to one another. All right, so essentially just what you need to understand over here is we are transitioning between a global and a local coordinate system. And we do have some sort of a transformation matrix available to do that. If we know what the angle of the body is, we can easily find either the local vector or the global vector of some sort of a point relative to some origin. Now, in our case, the pendulum rod is connected to ground. Hence, equation 714 expressed in matrix form becomes this minus R1A, which is equal to 0. So if I simply use this formulation that I have over here, it becomes minus x1, y1. So the location, the global coordinates of the center of mass of the pendulum, minus, because remember I'm now multiplying by a minus in front over here. So it becomes minus that xy, minus, and then I have my transformation matrix over here, considering the angle of body 1. And I multiply this then with this xi eta p over here. So it's also just good practice to include a subscript to define what body I'm working on. So xi 1a means that I'm working on body 1, and I'm interested in point A, and eta 1 is just then in the eta direction, once again on body 1, related to A. And this should then be equal to the 0 vector that I have over here in accordance with my kinematic joint, or my revolute joint function that I had originally. Now, enforcing these conditions forms a pin joint between the two bodies as shown in figure 7.3b. So you'll remember the previous figure that we had showed RIP and RJP separately. However, if we enforce this equation over here, which says RJP is equal to RIP, now we end up with the two vectors lying on top of one another. And this is essentially constructing the revolute joint that I'm working with. It is not a problem that in our case, with the pendulum rod, vector R1A cannot be depicted. Remember, R1A is the vector from the global coordinate system to, in this case, it's on body 1 to point A. So remember that since we have the global coordinate system lying over here, it simply means that R1A is equal to 0, since I don't have a vector, or I can't construct a vector over here. R1A is essentially 0. It's at the global coordinate system's origin. But this is not really a problem. We're just interested in how we're going to computationally create this constraint. Even if it is 0, our constraint equation should be able to derive properly, and we should be able to understand the underlying kinematics and dynamics of the system. Now, the two constraints in equation 714 reduce the degree of freedom between the bodies by 2. Now, this remains true for our pendulum rod, where phi r2 is equal to minus r1a, and this is equal to 0. Now, using equation 7.9, the velocity constraints for a revolute joint are obtained from the time derivative. So we simply take equation 714 and we derive with respect to time, and we then end up with this equation over here, which simply says that phi dot r2 is then equal to r dot ip minus r dot jp. And I can then go and expand this using my rotated vectors in this case, and I essentially end up with this second equation over here. Equation 7.9 is proven in PMD section 3.2.2. Once again, we're not interested in the proof. We just want to understand how we go from our base constraint equation to our velocity constraint, which is simply a time derivative. Equation 7.9, like we said, in our pendulum rod, it follows that the general equation for the velocity constraints can then be rewritten in this form over here. So we take equation 7.9, we substitute all of the placeholders in, and this is the equation that we end up with over here. And we can then rewrite the above equation in this form over here, 7.15. This simply combines body I and J with one another in the same matrix. So we just use a separation line over here to show when we're working with body I, when we're working with body J. But this is then the general form and how we can express it. And for our pendulum rod, equation 715 then reduces to this form that we have over here. And you might remember from the previous section that we also looked at this minus I minus S rotated 1A should look familiar. This is essentially, once again, the Jacobian matrix that we consider. And we can now, if we perhaps didn't have a case of the pendulum rod being connected to ground, if we had a case of two bodies which are connected to one another, the Jacobian matrix can be expressed in two separate submatrices, each pertaining to its specific body. So we once again have DI with the superscript R2. So we're still working with a revolute joint imposing two constraints, but DI is then applicable to body I, and DJ is then applicable to body J. In our case, since we're just working with the pendulum rod, so a single body mechanism, we can go and write D1, which is simply equal to minus I, and this minus S1A rotated. Now the time derivative of equation 7.15 then yields the acceleration constraints. So we simply go one step further, and this is then the system that we end up with. Once again, you can see just from going from the velocity to the acceleration, even for this simple pendulum rod example, the equations and the vectors that we use become quite complex. And this pertains to the generality of these general purpose algorithms, such as the DAP-BC workbench that we're going to use. In that case, it's going to generate this number of equations regardless of the number of bodies that you have. You're essentially always going to run through these time derivatives, and you're going to generate this system of vectors and matrices to solve your problem. And we can rewrite the above equation in this form as well. So we now know how the Jacobian matrix of the I and J bodies look. So we can simply simplify this first matrix that we have over here. The second part, or the vector that we have over here, essentially remains the same. And then we simply consider these forms over here, which is just essentially a multiplication of the matrix that we have over here together with the vector form. Since we have a zero vector over here, it does simplify to some extent as well. And for our pendulum rod, equation 717 then reduces to this form that we have over here. Once again, only working with one body, so we can ignore this DJ and this RJ, phi J components over here, so that we are only focused on body 1, or our actual pendulum rod body. And this is then once again equated to 0. This simply follows from the time derivative, where the right-hand side of the equation always remains at 0. Now, the right-hand side of the acceleration constraint, if we move some of these components around a bit, we essentially end up with these last two terms, which we can move over to the right-hand side, and this is then called this gamma parameter that we have over here. So gamma R2, which is then equal to the negative of these two components. And for our pendulum rod, equation 718 then reduces to this part that we have over here. So I essentially take this part, move it to the right-hand side, and it becomes the S1A rotated dot multiplied by phi dot 1. All right, so that was quite a lot of mathematics regarding the revolute pin joint. Like I said, we're not too worried about the actual derivation of these equations. We just want to understand we can essentially translate from a positional analysis to a velocity constraint analysis, and then to an acceleration analysis. And one of the components that essentially remains the same across them is the use of the Jacobian matrix. So it's a very versatile matrix to set up, very versatile to use when you're performing the equations or the computations. You essentially have a generated Jacobian matrix that you can apply to all the position velocity, and acceleration constraints. Now, going on to section 7.4, which is then the constrained equations of motion. With the presence of kinematic joints, we must consider the dependency of the coordinates, velocities, and accelerations through equations 750, 51, and 52. And these equations are then given over here. So equation 750 essentially starts with a sort of a positional constraint analysis. So phi being equal to phi as a function of c, and this is equal to 0. Equation 751 is simply the time derivative then of this case, so we end up with phi dot, which is equal to the Jacobian matrix D multiplied by C dot. And finally, if we go one step further, we can now essentially use the time derivative, and if we apply this, we just need to remember by the product rule, phi double dot is going to be equal to dc double dot. So the first one remains the same. I derive the second part, so the c dot, plus, and now the second part remains the same, so c dot remains unchanged, and I just have to go and derive d, which is then the Jacobian matrix. So this is why I get this dc double dot plus d dot c dot, and this is still equal to 0. Now, starting off with equation 750, for our pendulum rod, equation 750 can simplify to this form that we have over here. So phi is simply equal to minus R1A. This we saw from the previous section. And then C is simply our centroidal positions that we have available over here, x1, y1, and phi1. And then phi can also be expanded. So this minus R1A is then expanded also in accordance to what we looked at in the previous section. So I end up with this equation. And then if I want to do some simplification on the system, so if I rather want to use the global vector S1A instead of the local coordinate system vector, I can simply combine the transformation matrix with this local coordinate vector, and I get this minus S1AX, S1AY in the global regime, essentially. Right, equation 751 for our pendulum rod, 751 also simplifies to this form that we have over here. So once again, it's our Jacobian matrix multiplied by C dot. So C dot is simply x dot 1, y dot 1, phi dot 1 is also equal to 0. We know what the identity matrix should look like, and we know what the rotated version of S1A should also look like. And then finally, equation 752 for our pendulum rod, 752 is going to simplify to this form over here. Once again, we see the unique Jacobian matrix that forms over here. C double dot is now simply my x, y, phi vector that I have just double dotted. So I derived it twice with respect to time. Plus, and then I have this 0 minus s dot 1a rotated multiplied by the c dot vector that I had previously. And over here to the right, it just gives a breakdown of the expanded vectors as well. Now, furthermore, for a system of constrained bodies, the equations of motion must contain the reaction forces associated with the kinematic joints. So up to now, you'll notice that we've essentially focused on the kinematics. Now we want to start looking at the actual underlying dynamics, and this is a typical process that one follows whenever you set up a multi-body mechanism. Start with the kinematics, and once you have that figured out, then you move over to the forces and you do an actual dynamic analysis. So these reaction forces are included in the equations of motion, HR. So the superscript that you have over here, the R simply shows that you're working with a reaction force, while the applied external forces are included in the equations of motion as HA. So the A once again showing that it's applied forces that we're working with. And then we can go and write down equation 753, which is essentially an expanded version of the original Newton's second law equation that we considered, or the centroidal equation of motion that we considered. Now we simply break our external forces up into applied and reaction forces. Now for our pendulum rod, equation 753 can then be expanded once again, and you'll notice this looks familiar to what we had initially. And this is also what we did initially, is to break up the applied forces and the reaction forces. So the reaction forces were the lambda 1, lambda 2 forces, because we essentially remove the pin joint. We imposing those two forces or reaction forces over there. The applied forces in this case is simply gravity. Gravity being an external force that is applied due to the mass of the system. All right, now therefore, for a constrained multibody system, the complete set of equations of motion must be considered as equations 750 to 753. So these equations that we looked at, 750 up to 752, which is focused around the kinematics, and then 753, which then takes into account the dynamic analysis. All right, now we note that if there are NC independent constraints in equation 750, the number of degrees of freedom is then denoted as N subscript DOF, which indicates the number of degrees of freedom, is equal to 3 times N subscript B, so this is the number of bodies that I have in my system, minus N subscript C, which is the number of constraints. Now thinking of the pendulum rod, in our case, since we're working with a single planar body mechanism, if we look at the number of bodies, it's just going to be equal to 1. So it's 3 times 1 minus NC, the number of constraints. So remember that we allow rotation about that pin joint, but we don't allow translation between the two bodies in either the X or Y direction. So those are 2 degrees of freedom that I'm removing, essentially 2 constraints that I'm applying to the system. So if I had to go and calculate the number of degrees of freedom that I have, it would be 3 times 1 body minus 2 constraints, or 2 degrees of freedom that I remove. So 3 minus 2 is going to give you a single degree of freedom that I have in my system. And this makes sense if we consider the pendulum rod. It essentially only swings or rotates about the z-axis. So there's only a single degree of freedom available in any case. Now, knowing the coordinates and velocities of a system at any given time, the following can be evaluated. The constraints of equation 750, the Jacobian matrix D, then we can also find the array D dot C dot, and we can also find the array of applied forces HA. The arrays that then need to be determined numerically are the array of acceleration C double dot, and also the array of reaction forces HR. So essentially the kinematics of the system and the underlying dynamics due to reaction forces. In the body coordinate formulation, a systematic process can be followed to construct the array of reaction forces. The developed systematic process can enable a computer program to automatically construct the complete set of equations of motion for a multi-body system. Now, the array of reaction forces can be described in a different form by the method of Lagrange multipliers, borrowed from the optimization theory, as the reaction forces being equal to d prime multiplied by lambda, which is then the Lagrange vector that we have. So D is a system Jacobian matrix. Lambda is an array of coefficients known as Lagrange multipliers. The number of multipliers, that is the dimension of array lambda, is equal to the number of constraints, or the number of rows in D, the Jacobian matrix. So in our pendulum rod example, we have 2 constraints, so we expect that the dimension of the lambda array will also be 2. In other words, for each constraint, there is 1 Lagrange multiplier. And in our pendulum rod, equation 754 is then expanded as in this form over here, and you can indeed see that our Lagrange multiplier vector is 2 rows, corresponding to the 2 constraints that we impose on the system through the revolute joint. Now, the immediate advantage of describing the array HR as d prime lambda is that the number of elements in the reaction force vector is 3 times the number of bodies. but the number of unknown multipliers in the array lambda is in C. So we know that the number of constraints has to be less than 3 times the number of bodies. You can't really have a case where the number of constraints is greater than the degrees of freedom of your system. In that case, you essentially have an over-constrained system, so your mechanism will not operate. It will either be completely stationary, or it won't exhibit the motion that you expect it to move at. In our case, we're specifically also focused on multibody dynamics, so the actual motion of the system. So therefore, we want our constraints to be less than the number of degrees of freedom that our system has, so that we can look at the dynamic motion of an actual system. All right, but in any case, using this formulation over here, we essentially reduce the number of unknowns in the equation of motion. Now, for our pendulum rod, the number of elements in the reaction force matrix is 3, but the number of unknown multipliers in the array lambda is 2. So that is, we indeed have reduced the number of unknowns in the equations of motion. Now, with the new representation of the array of reaction forces, equation 753 is expressed in this form over here. So mc double dot is equal to our applied forces plus our reaction forces, which have now been expanded to d prime lambda. And for our pendulum rod, equation 755 can then be rewritten in this form over here. So now we utilize the Jacobian matrix, and we also utilize the reduced number of unknowns that we have through the Lagrange multiplier matrix or vector that we have available. And then to solve these equations for the unknown accelerations and the Lagrange multipliers, we simply append equations 752 to 755 to form the following set of equations. So you'll notice over here, essentially what we do is we had our original kinematic analysis followed by a dynamic analysis. In this case, we just combine them. So now we have a mass or moment of inertia submatrix. We have our Jacobian submatrices and its transpose. And then we have the C double dot, which pertains to the kinematics, and the lambda vector, which pertains to the dynamics. And this is then equal to the applied reaction forces and this minus d dot c dot system that we have over here. And then to the right, they also give us a breakdown of all of the expanded vectors, essentially. So the way in which we moved through these equations, systematically simplifying it, you can always go back and just check if I have this smaller vector, if I expand it, what do I expect to get over here? And a further detailed discussion on solving these equations, either as an inverse dynamic analysis or as a forward dynamic analysis, is then left for chapters 12 and 13. So remember that in inverse dynamic analysis, we prescribe the motion of the system. So what are the displacements in the system? And we want to measure what the resultant forces are going to be in the system. A forward dynamic analysis is simply the opposite of that. So in that case, we specify the forces on the system, and we want to see what the effect of that would be on the motion or the displacement, the velocity, the acceleration of the system. All right, so I think that then concludes section 7.4 and also section 4 of our first lecture for the pendulum rod example. So perhaps just to reiterate, the equations that we looked at over here, the derivations, are going to be applied purely in a computational manner. So they are already applied in the DAP-BC workbench. We're essentially just going through it to understand the underlying principles, to understand what parameters are important and what we can do to essentially alleviate the computational efficiency of our system. And we now saw that one of the important aspects is the Jacobian matrix that we make use of. Its derivatives, its transpose forms, all of those things can be used across the kinematics and the dynamics of the system. And it's essentially our building blocks for when we construct the computational analysis. It's a very versatile matrix at the end of the day. All right, so with that being said, I just want to open the floor for any questions that you might have. That is essentially everything that we did now for our first lecture. So if you have any questions, yeah, feel free to either place them under the chat messages, or you can raise your hand if you'd rather want to ask the question. Um, yeah, so I'll give you, I think maybe a few, maybe a minute or so if you have any questions. All right, I don't think we have any questions at this stage. It's as expected, I think, at this stage, like I said, very theoretical analysis of our systems. I think once we actually delve into the application examples and start looking at how this workbench is able to efficiently solve the problems, then it will place things in a bit of a better light, how powerful the underlying principles are. Right, but with that being said, then I think I'm going to end it here. And yeah, thank you very much. I'll see you then in the next lecture when we continue with the driven and undriven pendulum rod analysis. Right, thank you.